So again, Bluetooth Low Energy is one of the ones that is seemingly more common for some of the new wireless systems that are coming out. And you can get really cool stuff from this too. Because it is closer to the brain, you can get information that is much more detailed. So in this study, they had someone who was already implanted with these devices for medical reasons. And this was part of, I think, the BCI Olympics last year. And they were trying to get a measure of which finger the person with the implants was flexing. So you can see here with some feature extraction and just like the raw signals, you have fingers 1, 2, 3, 4, 5, and you can get a nice measure of which finger they were thinking of flexing, and then use that to control robotic devices. This is another type of use case where, in this case, what they were doing was using these electrocorticography electrodes to measure while people with traumatic brain injuries were reading a series of words. And in this case, the goal was to predict which of those words they were going to forget and which they were going to remember. And so they could actually end up classifying which of the words they were going to remember and which of the words they were going to forget. So that's one of the really cool use cases for implanted electrodes. But of course, these come with more safety risks. So again, the circuits really, really should have some type of current limiting hard built in. If you are ever involved in the design of these devices in any capacity, please make sure they do, because the risks of heating up your brain are much higher than the risks of accidentally heating up your skin. If it's for cognitive enhancement purposes, I say the risk is low because it is unlikely that in the current state it will go ahead with actually like implanting these for cognitive enhancement purposes, since the benefits in no way really outweigh any of the risks you'd be taking on by implanting electrodes into your brain. But the privacy risks are, again, even potentially a little bit higher than with the EEG devices, because the signal is so much cleaner. You get much more specific information about where it's happening in the brain, since it's directly on the surface. You can do things like tell what things people are going to remember, what things people are going to forget. And then there's the whole issue of anonymizing this data. Because your brain data is so closely linked to you, and because it's unique enough that you can do things like use it as a form of authentication or as a form of identification, it also means that when you generate all of this data, it's very difficult to actually keep it anonymous, because if at any point part of your data gets de-anonymized, the rest of it is very easy to de-anonymize afterwards. So if you are storing lots of sensitive data, making sure it doesn't have things like meta information about where you were when it was collected and at what time and at what research institute is quite important. And especially for some of the more portable ones, they are more useful if you have information about like what time of day you were using it and where specifically you were using it. But that might also make it much more difficult to store securely. There's a very strong parallel with DNA, where like it's really difficult to actually keep DNA data anonymous, because you continue to generate data sources that are not anonymous all the time, since it is actually just little bits of you that are being left places. It was a horrifying way to say that, I'm sorry. So now we're going to move on to, reading from the brain, summarizing the key takeaways from this. Signal transmission is really similar to other wearable devices. So there's nothing that is super, super unique about neurotechnology signal transmission that isn't true of, like Fitbits, or in the medical context that isn't true of like pacemakers. But the signals that they carry do carry information that is very unique compared to these other wearables or other medical devices. And that information is occasionally quite sensitive, or things that could be used maliciously. All right, now we're going to move on to brain stimulation, where the concerns are a little bit flipped, where most of the concerns are about things like safety. So you also get all kinds of degrees of invasiveness when it comes to the brain stimulating devices. The least invasive is something called transcranial electrical stimulation, where you take basically fancy saline-soaked sponges, or occasionally literally just saltwater-soaked sponges, strap them to your head, connect them to some kind of current generator, usually about like 2 milliamps, and you run the current between the sponges. Turns out the path of least resistance is often directly through your brain. Or you have the super invasive deep brain stimulators, which are electrodes implanted directly into deep brain structures, again, for now for clinical purposes. So the reason that running a current through your brain changes things is because of these action potentials. They need to reach a critical threshold before one of these all or nothing events actually happens. And so if you are running a current into an area, you can make it either easier or more difficult for these action potentials to occur. Or you can, depending on where you place the electrodes, make it easier for different brain regions to work in synchrony, or more difficult. This is only true for the transcranial direct current stimulation. There are also all types of different stimulating pulses that you can send. So you can send like alternating current pulses as well, which have different effects. Those are mostly for synchronization. So if you, for instance, wanted to promote one of the frequencies that is characteristic of like sleepiness, you could send an electrical current at that frequency and just make it easier for your brain to go into the sleepy state or the more awake state, whichever you prefer. Again, the signals are usually sent over Bluetooth. A lot of the time they're hardwired, especially if it's one of the direct current stimulators, because those are basically just a battery with some resistors built in. But a lot of them now are controlled by microcontrollers, which means that if there are any vulnerabilities in those microcontrollers, that you can gain access to them. You can change things like the current shape, the current duration, what the maximum allowable current is. And if it's if it is one of the devices that has electrodes in multiple positions at the same time, you could also change things like which part of the brain is being stimulated, just by telling it to stimulate in a different spot. So here on the left is an example of one of the things you might want to do with this type of brain stimulation. What you're looking at here, this little triangle-y bit, is someone's nose, and you have just a top-down view of their head. It's called the 1020 electrode positioning system. In red, you've got a cathode. In black, you've got an anode. So the cathode is like on your forehead. The anode is on your shoulder. This is something called the DARPA Accelerated Learning Paradigm online. Just need to make sure the bunny quotes go in the video. And so this is a paradigm that was used in a study once to help train drone pilots faster, where they were looking at a scene and trying to pick out what thing they were trying to actually focus on. And what they did was record their brain activity during like the first chunk of training, figure out which parts of their brain activity were changing as a function of training, and then use the electrical brain stimulation to make it change a lot faster. So they were actually managing to bring the training time down by a fair bit using this. On the right, you've got an example of a brain stimulator that I built. You've just got one wire going for the cathode, one for the anode, and a little dial to change the current on it. It's very fun. So the safety concerns for this one are quite low. It's not fun to burn yourself with the system, but it's also not really life-threatening. And the effects of the brain stimulation are quite weak. They can produce very cool effects, but if you wanted to, really stick it to someone and accidentally make the current run from their shoulder to their brain instead of their brain to their shoulder, worst case, they would learn something a little bit slower instead of a little bit faster. It's unlikely to be a huge issue. It gets to be a bit more of an issue in the clinical context where, like, if someone is using it as their depression treatment, you could potentially actually make their depression a bit worse instead of better, which is just not good. And again, privacy concerns. I have not seen anyone figure out how you can record brain signals directly from the brain stimulation technology. You'd have to build in actual recording systems in order to get some of that information back, because the resistance is just way too high from saline-soaked sponges to be able to read the brain signals back. So it's not really a privacy concern. And then you get into the more invasive stuff, the brain implants. So I'm going to break this down into 3 different categories. You've got motor, sensory, extrasensory, and cognitive. And these are in terms of the effects that they can have on the brain. And again, we're still working with the same type of signal transmission protocols as before. Okay, so this is an example of a sensory implant. It's called the Argus 2 retinal prosthetic. And what it does is it works much in the same way as a cochlear implant, if you're familiar with those in the context of hearing. We've got a little microphone and it stimulates the cochlea and lets people hear. But in this case, it's got a little camera that then stimulates the retina and lets people see again, which is very neat, but carries some pretty unique privacy implications, because in that case you do have a continuously recording camera, and it has to maintain a certain memory bank in order to actually be able to do the correct stimulation at the appropriate time. And if anyone remembers how horrifyingly the Google Glass went over in public spaces, people were very upset. There was someone that had it like torn off their face because they didn't like being recorded. So it's definitely something to consider when you are moving towards more invasive implants, that if you were to try to remove this, it would cause much more damage than a pair of glasses. And here's someone who was implanted with one of these devices and has since taken up a variety of extreme sports, including archery and heliskiing. But it works well enough that people can start, making out different shapes or like navigating in the real world, which is very cool. This is an example of one of the movement prosthetics. So in this case, she has electrodes implanted into motor cortex and is using her thoughts to convince this robot, not convince this robot, to directly control this robot so that it lifts up a glass and brings it towards her so that she can have a drink. And this has a few other applications as well. So for now, they've gotten it to do this. There's also research going on into complete remote robot assistant control. So instead of just controlling an arm that picks up a thing and brings it towards you, ideally people that have these implants would be able to just send a robot around their house to fetch something from the kitchen or other similarly useful things. Then you can get into some of the more cognitive stuff. This kind of bridges between the movement and the cognitive. What you've got on the left-hand side is a mouse that's being driven around with a remote control. So the mouse has electrodes that are implanted to subtly suggest that if it turns the way that the remote control is telling it to, it will get a brain stimulation reward. And these brain stimulation rewards are usually electrodes implanted directly into reward centers of the brain that release dopamine. So it's kind of like electrical cocaine. It sounds horrifying. They're really useful for search and rescue, apparently. Mice can get lots of places that cars can't. You can also do the same thing with moths. So there are some cool videos online of people driving moths around because they've been implanted with electrodes. And then on the right, you've got something that's kind of similar, but in the context of a larger animal. And this is research that was done back in the 1970s. And it was sort of the first example of brain stimulation being used to control something, where the bull is implanted with electrodes in areas of the brain that are related to aggression and motor planning and a whole bunch of other things. It wasn't a super well-controlled study. It was the 70s. And the researcher is actually the one on the right. He's holding a remote control. He decided that the way to test his theory that brain implants could be used to control behavior was to jump into a bullfighting ring with a remote control and a remote-controlled bull. Yes? So to summarize risks and consequences, the safety risks are pretty high, especially if the circuits are not built super well, or if power consumption becomes an issue. Eventually power sources get hot. There's also a risk of infection when you implant these. When you take the implants out, there's always a risk of infection when you're opening up people's skulls, unsurprisingly. But then it does also carry the additional risk of behavior modification. So it doesn't have to be something as dramatic as the remote-controlled mouse in the case of a person. That would be really difficult to do. I'm sure most people would notice if you were subtly giving them suggestions to, turn left and then shocking their brains. It's much more easy to do with a mouse. But if you are worried about things like, hacking cars, if everyone all of a sudden has these brain implants that connect their brains to the internet, it does also carry the risk that, especially for movement control, you might be able to temporarily take control over someone's arms or something like that. So just making sure that any implants that are doing something useful can also be used to do something not great if someone gains access to them that shouldn't. And again, privacy is a pretty low risk because they are built for stimulating as opposed to recording, and unless you build in recording electrodes, you're not going to be getting information back from them. But you can always build a closed loop system, which has the best of both worlds, but also the worst of both in terms of safety and privacy concerns. So if you remember the study I talked about where they were recording activity during word recall and figuring out which words people were going to forget, the second part of that was actually that they had brain stimulation on hand and were eventually able to train a system to detect when someone was going to forget one of the words that they were reading and apply a brain stimulating current to help them not forget it. So they were actually able to significantly increase this thing called free recall in the traumatic brain injury patients, which is really, really cool. So this carries a lot of implications for future directions, especially in terms of non-clinical applications like merging with artificial intelligence, which seems to be the goal of a company called Neuralink, run by Elon Musk. If you haven't looked into it, you should. It's a bit of an interesting read. So in terms of developing these applications, they're still quite far off, in no small part because it is very difficult to get ethics approval for implanting things into people's brains unless there's a very compelling clinical reason to do so. So what most of the groups that are looking towards human enhancement are doing is working in clinical populations for now and trying to develop new sorts of sensors that will be less risky so that you can move into non-clinical contexts, which carries its own set of ethical concerns with it, since historically, using people as guinea pigs for the purposes of human enhancement has not gone great. In terms of mitigation strategies, one of the big ones is to keep the hype about what brain-computer interfaces can actually do to a minimum so that people are not likely to take on huge risks for very marginal benefits. So for instance, it is really cool that you can implant things to modify behavior in clinical contexts. That does not necessarily mean that you should go out and try to get a brain implant so that you can remember more words in a day. That is not a particularly great trade-off for having an implanted device in your head. Make sure that people understand their data sets. If you do ever get approached to do contracts related to medical devices, start at the level of what data you're collecting, because if people are storing raw data, you might not necessarily know what sorts of signals you'll be able to predict later on. So making sure that things are secured at every stage, not just at the database storage stage, is important. If at all possible, keep devices off the internet unless there's a very compelling reason not to do so. I feel like that's probably just good advice in general for electronics, but especially true for brains. And store data locally as much as possible. Again, you don't necessarily know what sorts of things people will be able to predict from your brain signals in the future, so keeping the data local might be a good plan. Good. So neurotechnology, not uniquely vulnerable to hacking, but still vulnerable to hacking. The consequences are potentially worse than usual. If it can help you by making your arm move, it can probably also hurt you by making your arm move, or any such similar things for all of the types of applications. So maybe think about what use cases you actually need brain stimulation for or brain recording for before incorporating it into things. Good.